the current year assignment problems. So these solutions may help you. Can you see the screen?
Yes, sir.
Thank you. So let me show you the assignment problems firstly. So here is the first problem. So the first problem is, let A be a symmetric matrix of order 3 with a distinct eigenvalues. So it is given only that A is of order 3 cross 3 and it is symmetric. That is the only thing hypothesis given. So then which of the following can be the eigenvalues of eigenvectors of A. So we have a property that whenever A is symmetric, we have that eigenvalues are orthogonal to each other. So by using that condition, we will check each option here, which one is the correct option. So the first option is given A is 3 cross 3 and A transpose equal to A. So from this we know we can say the eigen vectors of A are orthogonal. So from among the options we will check which one is the set which contain orthogonal vectors.
Sir, can't hear your voice.
Oh, is it? It is on.
No, we can hear, sir.
Yeah, please check that person. Maybe your audio problem. So the first option, somebody is still joining. So the first option is -1 1 0. So I'll explain that the first option here only. So from this, for the first option, we can see easily that if we take these first and last vectors, these two vectors also
Sir, your voice is not audible.
Your voice is breaking actually.
Can you hear me now? Hello?
Sir, I can hear you, sir, clearly.
Yeah, maybe the other people's. Can you hear me? That person.
Yes, sir. Now.
Yes,
That
sir.
person.
Yes.
Yes, sir.
Yeah. So for the first option, I'm taking the first and last vectors. Actually, we have to check for each vector, each two vectors. But for the first and second and third, actually the second and third also not linearly. Not orthogonal. I'm just checking the first and third vectors. These two are orthogonal or not. So for the first option, I'm just checking this one. The third vector is 2 2. Sorry, actually these two are orthogonal. So let me take the second and third one. 0 0 3 and 2 2 minus 1. So I'm just checking these two vectors are orthogonal or not. So by standard inner product we have this equal to -3, which is not equal to 0. So this set is not eigenvectors. This set is not the set of eigenvectors of A. So this is not the correct option. So for the second option, can you tell me which vectors are not orthogonal? Which two vectors? Can you guess by just simply looking at the vectors?
101 minus 120
Yes.
is not equal
And
to 0.
third, -120 010.
Yes. So this equal to -1, which is not equal to 0. Similarly, for the third option, we can take the second and third vectors because the first and second vectors are orthogonal. So I'm just taking the second and third vectors. 3 minus 1 0 minus 2 comma 1 comma 1. This is equal to minus 6 minus 1. This is equal to minus 7, not equal to 0. So the first three options are not eigenvectors of matrix A. Because of the symmetric property, we can say that. So for the remaining option is the only correct option, fourth option. Of course, we have to check this also. So let me check that here only. So the first, I'm just checking for the first two vectors. Minus 2, 2, 1. This is equal to minus 2 plus 2, that is equal to 0. And for the second and third vectors, we have minus 2, 2, 1, comma 1, comma minus 1, comma 4. This is equal to minus 2 minus 2 plus 4. This is equal to 0. And similarly for the first and third vector, 1, 1, 0, 1 minus 1, 4. This you can check. This is also equal to 0. So the fourth option is the orthogonal set. So we can say this can be the eigenvectors. This set forms the eigenvectors of A for some matrix A, not for each matrix A. So fourth option is the correct. So the second problem here is, let A be a skew symmetric and diagonalizable matrix of order 5. It is given only that A is skew symmetric and diagonalizable. We have to solve this problem by using these two properties only. So whenever for a real skew symmetric matrix, we have the trace of A equal to 0. Can anybody know the reason why it is? Because A is,
All the diagonal elements are zeros.
yes, whenever A is real skew symmetric, then we have all the diagonal elements are zeros. Skew, real skew.
So because skew symmetric matrix has
Yes,
zero
correct.
diagonal elements.
Yes, yes, correct. So and it is diagonalizable also. So that means A is equal to P times some diagonal matrix into P inverse, where D is diagonal matrix. By using these two properties, we will solve this problem. So it is asked that determinant of e power A. Let me solve this separately. See the question for this, see the problem for the solution of this. So for the second problem, we have that trace of A equal to 0 and A equal to P inverse, what I wrote, PD P inverse or P inverse DP? PD P inverse, okay. PD P inverse, where D is diagonal matrix. In fact, the diagonal elements of this D are nothing but the eigenvalues of A.
Sir, why can't it be P inverse DP, sir?
Yeah, it can
Why
be taken.
can
Yeah.
be taken up? Okay.
Yeah, suppose you take Q equal to P inverse, then I can write A equal to Q inverse DQ. That can be possible. You can write anyway.
Thank you.
So it is asked to calculate determinant of e power A matrix. So here we will see that since A is diagonalizable, we can say e power A is also diagonalizable. Can anybody say that why it is? Anybody know the reason?
Because it is the sum of the diagonalizable matrices.
Yes.
E power A is 1 plus A by 1 factorial plus A square by 2 factorial.
Yes, right. So we have that e power A equal to I plus A plus 1 by 2 A square plus 1 by 3 factorial A cube plus and so on. And here all the matrices in this summation I, A square, A cube, all are diagonalizable. So we can say e power A is also diagonalizable. So we can say that whenever e power A is diagonalizable,
So please repeat it. So please repeat it.
yeah, okay. So we have that e power a is nothing but this expression, I plus a plus 1 by 2 a square plus 1 by 3 factorial a cube plus and so on. Here we have that all the matrices I, a square, a cube, all are diagonalizable. That means for each matrix we have that we can write PD, sorry, here I, Pi, P inverse plus PA, this is PD, P inverse plus 1 by 2 times P d square P inverse plus and so on. Like for next a cube we will get PD cube P inverse. So we can say that this is equal to P times I plus d square by 2 plus and so on into P inverse. So we can say this is equal to P times some other matrix, some, let me write M. This is equal to M into P inverse. So where M is nothing but the diagonal matrix. So we can say e power a is also diagonalizable. Do you understand now? Or do you still have doubt? Otherwise I will proceed with this. So okay, so this here M is nothing but e power d, that you can see. So from this we can say determinant of e power a is nothing but determinant of p e power d p inverse. Here p is invertible, so from that property we can say the determinant of this p e power d p inverse is nothing but determinant of e power d. So from this, and we have that D is nothing but a diagonal matrix whose diagonal elements are the eigenvalues of A. So we have that, how to say, like here. So we know that determinant of e power a is nothing but product of eigenvalues of e power d. So whenever lambda is an eigenvalue of a, sorry, some eigenvalue of a, then we have e power lambda is nothing but eigenvalue of e power d. So by using that property we can say this is nothing but equal to e power lambda 1, I am saying lambda 1 times e power lambda 2 times e power lambda 3 times e power lambda 4 times e power lambda 5, where lambda 1, lambda 2 and so on lambda 5 are eigenvalues of a, not d. Sorry, of course the eigenvalues of a and d are same. So by this we can say this is equal to e power lambda 1 plus lambda 2 plus and so on plus lambda 5. Here we have that lambda 1, lambda 2 and lambda 5 are eigenvalues. So there is nothing but the
Trace of A.
Yes. So by the property that we have skew symmetric, so we can say trace of A equal to 0. So by that property we write e power 0. This is nothing but 1. So the determinant of the matrix e power A is nothing but 1. Is it okay, or anybody have any doubts?
Clear, sir.
Yeah, thank you. So the option is B, correct. So for the third problem, which of the following statements is not correct? So we have to check the false statement. It is given here that P is orthogonal matrix and V is inner product space. So the only property we have that P is orthogonal matrix. Can anybody tell the definition of orthogonal matrix? P is orthogonal matrix. Yes, please.
Norm is equal to 1.
Yes, actually that is one property, actually not the definition. Inner product space. So we say a square matrix P is orthogonal matrix when P into P transpose equal to identity, or we can even say P inverse equal to P transpose. From this property only we can say. From this property only we can say it is confusable. This symbol. Okay. So by using this, we will check the options. So the first option here is P square is orthogonal. So we have to check whether P square is orthogonal or not. That means we have to check that P square times P square whole transpose equal to identity or not. That we will check. P square times P square whole transpose. We have that A power n whole power transpose is nothing but A transpose whole power n. So I'm just replacing the power on transpose here. We have this property. So by this we can rewrite this as P times P and P transpose times P transpose. By associative property we have that P into P transpose into P transpose. So we have that the first condition here it is. So by this we can say this is equal to P times I and P transpose. This is I. So by the same property we have that this is equal to I. So we have P square into P square whole transpose is nothing but identity. So from this we can say P square is also orthogonal. Second property, second option that is asked that norm of PU equal to norm U or not. Second option is actually it is asked to find out the false statement, but first option is correct, so that is not the answer. Second option is norm of PU is equal to norm U for every U belongs to the inner product space V. So we have to check that. We have a property that, not a property, actually this is the definition. Norm of PU square is nothing but the inner product of the matrix PU and PU. So by this definition of this we have that this is nothing but determinant of P into P transpose into U comma U, the inner product of U comma U. So by the property that we have P into P transpose is nothing but identity, so the determinant of identity matrix is nothing but 1. So again we have this equal to U comma U. So from this we can say norm U square. Here the norm is positive quantity. So whenever we have two squares of two positive quantities are equal, we can say those two quantities are equal. So by that property we can say norm of PU is nothing but norm of U for every U belongs to the vector space V. Sorry, inner product space here. So second option is also not the answer, but of course the option is correct, but not according to this question. So the third option here is P inverse Q square whole transpose may not be orthogonal when Q is orthogonal. So it is given that Q is orthogonal and P is also orthogonal. So we have to check P inverse Q square whole transpose is orthogonal or not. P inverse Q square whole transpose. We'll see that. So third option is P inverse Q square whole transpose. We have to check this is orthogonal or not. So to check this, we'll consider the matrix into its transpose. Its transpose is nothing but the matrix itself only. Transpose whole transpose. So we have this is nothing but, so we have the property that whenever AB are two square matrices, we have AB whole transpose. Let me write with red pen. AB whole transpose is nothing but B transpose into A transpose. So by using that property we can write this is nothing but Q square P inverse, and here it is, sorry, Q square transpose q square whole transpose p inverse whole transpose, and here this is nothing but p inverse q square. So we have that this is q transpose whole square, this is p transpose whole inverse, and this is transpose, that is inverse, into p inverse q square. We have that p and q both are orthogonal, so we can write this as q transpose. This is p into p inverse whole, sorry, p into p transpose whole inverse, p into p transpose whole inverse into q square. This can be written as q into q, q into q. So we have that middle term p into p transpose is nothing but identity. So we can write this as q transpose, q transpose, q, q. Again we have that q is orthogonal, so we can write this as equal to identity by the property of orthogonal. So we can say what is that matrix? P square q inverse, p inverse q square.
Sir, one doubt, sir.
Yes, please.
If P is orthogonal, is its inverse also orthogonal?
If p is orthogonal, yes, of course. Yeah, let me prove that. 1 minute. Is orthogonal. So we have that p is orthogonal. That means p into p inverse, sorry, p into p transpose equal to identity. Or we can say p transpose is nothing but p inverse. So we have to prove that p, what did you ask? P transpose or p inverse? I think p inverse.
P inverse.
So yes.
P
So,
inverse into P inverse transpose.
yeah. So we have to check that p inverse into
P inverse transpose is equal to I or not.
Yes. So this is p inverse. This is transpose. This is equal to p inverse times this is p transpose whole inverse. So we have that this can be written as p transpose into p whole inverse. This is equal to nothing but I. Yes.
I, correct.
Yes.
Thank you, sir.
Yeah. So this is about third option. Actually, it is, we proved that p into, sorry, this option, the matrix in the third option is orthogonal, but the option it is given that may not be orthogonal. That means they are saying it need not be orthogonal, but we have proved that it is orthogonal always. So this is the wrong option, but they are asked about false statement. So we can say the third option is the correct. And for the fourth option, we can directly say that by similar to the second option, we have p u comma pv is nothing but determinant of p into p transpose into u comma v. So we have that p is orthogonal. So we can say this is nothing but u comma v for every two vectors u and v in v. Is it clear? Anybody have any doubt in this problem?
Okay.
Yes. Okay. Thank you. So the fourth problem is given a matrix A, then the range of eigenvalues of A. So here we mainly use one theorem that, what is the name of that theorem? Yes, Gertzgorian theorem. Can anybody state that theorem? Anybody remember that? Let me write the matrix 2 minus 1 0. This is fourth problem. A equal to 2 minus 1 0. 3 minus 1 minus 2, 3 minus 1 minus 2, 3 minus 1 minus 2 minus 5, 1, 1. So it is asked the range of eigenvalues of A. There is one simplest method. If you don't know, you can directly find the eigenvalues of this matrix and you can check the options. But that is a very lengthy process. So here we use one theorem, that is Guts-Gorin theorem. Name is difficult. Guts-Gorin circle theorem. Nobody knows the statement of this theorem? Okay, let me state that. So we have that whenever A is a square matrix like A11, A12 and so on, A1n, A21, A22 and so on, A2n, AN1, AN2 and so on, ANN. For this matrix, the range of the eigenvalue, when suppose lambda is eigenvalue, lambda is eigenvalue of A, then we have that lambda minus AII, the modulus of this quantity is always less than or equal to summation of the elements in that particular ith row except that II, that is nothing but j is equal to 1 to n, j should not be equal to I, modulus of Aij. That means what we have to do here is that, let me take that one. So whenever lambda is an eigenvalue, we have that lambda minus A11, the diagonal element, the diagonal element in the first row. This has to be less than or equal to the summation of the remaining elements in that first row except that diagonal element. That means, let me write clearly, this is less than or equal to A12 plus A13 plus and so on plus A1n. Similarly for the second row also, lambda minus A22 has to be less than or equal to A21 plus A23. Here, okay, here we remain with only 1 2 and 1 3. For the third row also, for the this I am saying for the given matrix, we have that lambda minus A33 has to be less than or equal to A31 plus A32. So by these three properties we will check the range of the eigenvalues. So let lambda be an eigenvalue of A. So by that we can say lambda minus the diagonal element in the first row has to be less than or equal to, the first row is nothing but diagonal element in the first row is nothing but 2. So we can say lambda minus 2 has to be less than or equal to the sum of the remaining elements under modulus. Of course there is only one non-zero element, that is this minus 1, so its modulus has to be, here I did not write the modulus, sorry, here modulus has to be there. You can see that modulus I have written here. I have written the modulus here. So by this property we can say this is less than or equal to 1. Similarly by using the second row we can say lambda minus something, the middle element, lambda plus 1 less than or equal to mod 3 plus modulus of minus 2, that is equal to 5. So lambda plus 1 is less than or equal to 5. Similarly lambda minus 1 has to be less than or equal to 6. Yes, any doubt? So by this we can say minus 1 has to be less than or equal to lambda minus 2 has to be less than or equal to, let me write in next line, that implies minus 1 has to be less than or equal to lambda minus 2 has to be less than or equal to 1. That implies we have to add 2 on 3 sides. So if we add 2 we'll get that this is 1 less than or equal to lambda less than or equal to 3. By the second inequality we have that minus 5 less than or equal to lambda plus 1 less than or equal to plus 5. So from this we can say minus 6 less than or equal to lambda less than or equal to 4. Similarly, we say minus 6 less than or equal to lambda minus 1 less than or equal to plus 6. That implies minus 5 less than or equal to lambda less than or equal to 7. So from among these three, we will get the upper bound for lambda. That means, so by these three right side inequalities, sorry, this, sorry, by these three inequalities, we can say lambda has to be less than or equal to 7. And similarly, by these three inequalities, left side inequalities, we can say lambda has to be less than or minus 6 has to be less than or equal to lambda. So we can say totally that
2 na 2
what
2 sir.
where
No, because here lambda is less than or equal to 7. From this lambda is less than or equal to 3, but it has to be greater than 1.
yes,
Then is lambda equal to 2? I'm just asking.
it can be equal to 2.
Uh,
It can be, but it can be equal to 5
it
also.
can it can
Yeah,
be equal to 5 also. How 5? Because here lambda less than or equal to 3.
here by this we can say only, yes, you are right.
We are talking of a single lambda only, no sir?
Yes, yes, yes.
Mhm.
So from this we can say, what is the answer? We can say upper bound or
Lambda
lower
equal
bound.
to
Yeah, tell me.
is lambda equal to 2? Is lambda equal to 2?
We cannot say correctly. It can be 1 also, it can be 2 also, 3 also. We cannot say
Oh,
particular this is the lambda. It can be
okay.
fraction also, rational also, irrational also. But we are
Okay.
searching for bounds only here.
Okay, sir.
So from this we can say lambda is less than or equal to 7 and this is less than or equal to 6. Is this correct? I think so. Let me check the options. Yes. So is there any doubt in this problem? Let me show you the solution, then you can ask. Yeah.
Sir, we got 3 bounds, no, sir? 3
Yes.
different.
Yes. Yes.
How can we say 3 different for single lambda?
Actually, here lambda means only one eigenvalue only. For the
Oh,
other eigenvalues, this for one eigenvalue this can be true. For the another eigenvalue, this can be true. The second inequality.
oh, okay, okay. Then
But
it's correct.
yeah, for
Oh,
combining all the eigenvalues, we can say this.
okay.
You just see that theorem statement, you can understand in that class notes. You can understand that clearly.
Okay, sir. Thank you.
So the fifth problem. It is given A is 1, I, minus I and 3. It is asked that norm of A square, norm of A2 square equal to alpha plus B beta root 2. So the value of alpha plus beta. Can anybody say how it is defined, that norm of A2 square? 1I minus I 3.
Is it some Hermitian matrix?
Yes, 1I minus I 3. Yeah, the matrix is Hermitian. What is the definition of norm A2 square? How it is defined? Anybody, if anybody is following the class notes, can guess this sixth problem. Okay. Can anybody here? This is nothing but the largest eigenvalue of not a, eigenvalue of a power h a. Here a power h is nothing but the conjugate, that is nothing but conjugate transpose. So firstly we will calculate what is the value of a power h a. From that matrix we can derive the eigenvalues and we will see. So here firstly we will see a power h, that is nothing but the a power, this is nothing but a conjugate whole transpose. This is nothing but 1 minus I 3 whole transpose. Conjugate is nothing but we have to do the conjugation to each and every element in the matrix A. By this we can again say that this is nothing but A. So the matrix A power h times A is nothing but A square. So it is asked that the largest eigenvalue of A square. So we will calculate the matrix A square. 1 I minus I 3 into 1 I minus I into 1 3. This is nothing but, can anybody tell, 1 plus 1 2 1 plus 3 I plus 3I, this is 4I minus I minus 3I minus 4I 1 plus 9, this is 10. Is this correct?
Yes, yes.
Yes, okay, thank you. So this is nothing but A square. So to calculate the eigenvalue of this, firstly we will calculate the characteristic polynomial of A square of x, not A of x. So this is nothing but the derivative of 2 minus x 4I minus 4I 10 minus x, the determinant of this matrix.
Sir, please, how did you write this, sir? This determinant 2 minus x 4i1.
Yeah, we have that
Lambda, you have taken lambda as x, is it? A minus
Yeah.
lambda is equal to 0. Characteristic equation.
Yes, not equal to 0. Characteristic polynomial, that is just a polynomial, not equation. So this is nothing but a minus xi, or you can write determinant of xi minus a also, whatever it is. I'm just taking polynomial. It is a polynomial, so we should not write it is equal to 0. If we write this becomes an equation, not a polynomial.
Then it becomes characteristic equation.
Yes, characteristic equation. So this is nothing but 2 minus x times 10 minus x minus 16 plus 16 square. It will become 16. So by solving this we get sixth problem. This is sixth problem, right? So this is nothing but 20 minus 12x plus x square minus 16. So this is equal to x square minus 12x plus 8. So eigenvalues has to be, can you solve this polynomial? This is just second degree polynomial. So we have that implies x has to be equal to minus b is nothing but 12. So plus 12 plus or minus square root of b square, that is 144 minus 4 times 32 by 2. This is equal to plus 12 plus or minus square root of, what will we get?
112. Square root of 112.
This is 6 plus or minus square root of, how can we write this? 112. Can we write this anything?
3. Square root of 23.
Are we making any error? I think something mistake is there. Is the product multiplication, matrix multiplication is correct? 2, the third element, can you check that minus 4i, is that correct? Minus I minus 3i, okay, correct. So, okay, can you tell me how it can be written?
Square root of 23.
23. How?
No, 4 root 7.
So that means it can be written as 2 root 7. We are dividing by 2. Square root of 23 is very large. Yeah. Yes.
Okay.
So that means eigenvalues are 6 plus 2 root 7 and 6 minus 2 root 7.
Sir, how did you write square root of 112 as a
Yeah.
square root of 112 is what?
Yeah. You tell me.
It's 23 into 4.
23,
Square root of 4 is 2.
23 into 4.
Hmm.
2.
Square root of 4 is 2. That you are taking it outside.
23 into 4 is 92 only.
Then how is this
16 into 7.
16
Root
into
of 16 into 7. Root 16 means 4. 4 root 7.
Yes.
okay.
So eigenvalues are these two. So among these, you can check 6 plus 2 root 7 is the eigenvalue. That means we have that alpha plus beta root 7 is equal to 6 plus 2 root 7. I think it is the question asked. Sorry, no, sorry, it is fifth problem. Okay, alpha plus beta root 2. Root 2. Something mistake is there. I think we should get here it is 4, not 8. So it will become 4ac minus 16. That means 128, right? Yes. So now how can you write 128? 4
64,
times
64 into 2.
okay, 64 into 2. So this means 8 root 2, that means 4 root 2. 4 root 2 minus 4 root 2. So from this we can say alpha plus beta is equal to 6 plus 4 root 2. So alpha plus beta is nothing but 10. So the acceptor is 10. This is about fifth problem. The sixth problem is also similar if we know the definitions of these two. If you are following the classes, we can simply get the what are the definition of these two matrices, these two terms. Let me correct the problem number. Actually, this is fifth problem. Given A is, does anybody have any doubt in fifth problem? Otherwise, I will proceed with the sixth problem.
No, sir.
No, sir.
Okay. So the matrix given in sixth problem is 1, 2, minus 4. 1, 2, minus 4. minus 2 3 1 2 0 minus 1 minus 2 3 1 2 0 1. So it is asked to calculate that norm of A1 plus norm of AE square, I think. Let me check that once again. Yes, A1 and norm of AE square. So can anybody tell what are the definitions of norm of A1 and norm of AE? Can anybody?
Norm of A1 will be maximum of J is equal to summation I equal to 1 to M mod Aij.
Maximum of J?
Maximum over J, where
Yes.
summation I running from 1 to M mod Aij. J running
Mod.
from 1 to N. If it is an N by N matrix.
Yes.
When
And for
coming
this,
to norm AE, the
yes,
value will be double summation mod Aij square whole power 1 by 2, where I running from 1 to M and J running from 1 to N. And
yes,
also we can say it will be equal to trace of A transpose into A whole power 1 by 2.
yes, correct. But of course, this is equal to nothing but trace of
Trace of
A
A
transpose
transpose
A.
into A whole power 1 by 2.
But here it is lengthy calculation to do the multiplication of A transpose into A. So we'll calculate this expression. So for the first norm A1 is nothing but the maximum of what this tells is nothing but the modulus of elements in each column. That means the elements in the first column are 1 minus 2 and 2, that you can see. This is nothing but the summation of modulus. This is nothing but the summation of modulus of each element. That means we get 1 plus 2 plus 2 comma 2 plus 3 plus 0 comma 4 plus 1 plus 1. So maximum of this is nothing but, actually we have to remove the j here because we wrote the elements directly. So this is nothing but 5, 5 and 6. The maximum is nothing but 6. That is nothing but norm A1. Similarly, norm AE square is nothing but summation, double summation I equal to 1 to n, j is equal to 1 to n, modulus of Aij whole square. Here we are doing the square to each element. That means we have to square each element and have to add some of them. So from that we can get 1 square, 2 square, 4 square. So 1 square plus 2 square plus 4 square plus 2 square plus 3 square plus 1 square plus 2 square plus 0 square plus 1 square. This is nothing but 1, 4, 5, 16, 21 plus 6, 21 plus 4, 25, 34, 35, 39, 40. So this is 40. So it is, the answer is norm A1 plus norm AE square is equal to 46. Is it okay? Anybody have any doubt in this?
No, sir.
No, sir.
Okay. So let us see the seventh problem. What is the time actually? Okay, we have 10 minutes more. So here we can see that the option is 46. So here it is given that consider an inner product on P2 defined like this. Inner product of two polynomials P and Q is equal to integration 0 to 1 P of x Q of x dx. Then which of the following pairs of polynomials in P2 are orthogonal to each other? We say two polynomials are orthogonal whenever inner product of those two polynomials are equal to 0. That we have to check for all these options. So let me write here only. So for these two problems, for the first option, we have that inner product of P comma Q is equal to integration 0 to 1. So by doing multiplication, we get here that x cube minus, sorry, this is x power 4, x power 4 minus x cube plus x square dx. So this is nothing but integration. By doing integration, we get x to the power of 5 by 5 minus x to the power of 4 by 4 plus x cubed by 3 over the limits 0 to 1. This is equal to, we get, of course this is not equal to 0, some non-zero quantity we will get. So this is these two polynomials are not orthogonal. Similarly, we will check for the second option. We will get that inner product is equal to integration 0 to 1 2x square plus x minus 6x minus 3 into dx. This is equal to, by doing integration, we will get 2x cube by 3 plus x square by 2 minus 6x square, sorry, okay, minus 6x square by 2 minus 3x over the limits 0 to 1. This is also not equal to 0, that we can check. Similarly, for checking the other options, we will get the answer. That is nothing but the fourth option, that we can do easily. Just some calculations is required. Can you check this, or you want me to solve?
No, sir. Okay, sir. We will do it.
So that we can proceed with other problems. So consider the set W equal to given three vectors in R power 4. So a vector alpha, beta, gamma, delta belongs to will be orthogonal to W if we have to check the options. Not actually options, we have to calculate the two equalities. We say that two vectors are, we say a vector is orthogonal to a subspace if it is orthogonal to each vector in that basis of that corresponding subspace. Actually here it is not the subspace, it is just a set. So it has to satisfy that the vector given alpha, beta, gamma, delta has to be orthogonal to each and every vector in the set W. So that means, let me write the vectors firstly. 1 0 minus 1 0. So W is equal to 1 0 minus 1 0 1 3 minus 4 minus 2 1 3 0 comma 1 comma 0 comma minus 3, I think. Let me check this once again. 0 minus 1 0 3. This is 0 minus 1 0 3 is a subset of R power 4. This is 8th problem. So given alpha comma beta comma gamma comma delta belongs to R power 4 is orthogonal to W. That means the every two vectors corresponding, the every vector to, I mean the vector alpha, beta, gamma, delta has to be orthogonal to each and every vector in W. That means the inner product of alpha, beta, gamma, delta, comma 1 0 minus 1 0. This has to be equal to 0. Similarly, the two equalities we will get 1 3 minus 4 minus 2. Sorry, I should write the vector first. Alpha, beta, gamma comma delta into 1 3 minus 4 minus 2 is equal to 0. Similarly, alpha beta gamma delta comma 0 minus 1 0 3, this has to be equal to 0. So this is under usual this inner product, so we will get that alpha minus delta equal to 0 from first equation. Yes, so
Second one,
yes, alpha plus 3 beta
3 beta minus
minus
4
4
gamma,
yes,
gamma,
minus 2 delta
2
equal to
delta
0. Third one is minus beta
minus
plus
beta.
3 delta equal to 0. Yes. So from this we get alpha equal to gamma, beta equal to 3 delta. We substitute these two values in second equation. From that we get alpha equal to gamma. It means alpha plus 3 beta. So beta is 3 delta. So this will become 9 delta minus 4. Sorry, delta, right? Yes. This is 4 gamma minus 2 delta. This is equal to 0. From this we get 3 gamma plus 7 delta equal to 0. That means gamma is nothing but 7 delta divided by 3. By substituting this here in this equation, we will get that alpha equal to 3 times, sorry, alpha equal to directly this 7 delta divided by 3. That implies 3 alpha minus 7 delta equal to 0. Similarly, beta is equal to 3 delta. Beta is equal to 3 delta. We don't have any equation for this. Let me check the options. From that we can get some confirmation. We got that 3 alpha minus 7 delta equal to 0. 3 alpha minus 7 delta equal to 0. That we don't have. 3 alpha or gamma. Yes, actually we have that alpha equal to gamma. So from that we can say 3 gamma minus 7 delta equal to 0. So this is correct option, but of course we have to check the first equation also. That we will check. That is related to alpha and beta. So we will substitute the value corresponding to that alpha and beta. So from this we get delta is equal to 3 gamma divided by 7. Beta equal to 3 times gamma. Gamma is nothing but 3 7 divided by 3. This is 3. 3 times 3 gamma divided by 7. 9 gamma divided by 7. That means 7 beta equal to 9 gamma. We have that gamma equal to alpha. So from that we can say 7 beta minus 9 gamma equal to 0. So this is alpha. Of course, for delta, this gamma also it is equal to 0. But to check the options, I'm just replacing that with alpha. So this is the correct option. Is it clear? Any doubt?
No, sir.
Okay. So time is almost over. I'll just simply explain the remaining two problems, how to solve, that you can solve yourself. The ninth problem here, it is given three vectors v1, v2, v3, and defined three vectors again, w1, w2, w3, like this. w1 equal to v1, w2 equal to v2 minus alpha w1, w3 equal to v3 minus beta w1 minus gamma w2. This is nothing but he is checking that you know that what is that theorem, Gram-Schmidt theorem or not. If you know that theorem statement, you can directly solve this problem. By that problem we have w1 equal to v1, w2 equal to v2 minus inner product of v2 comma w1 divided by inner product of w1 comma w1 into w1. Similarly, w3 is equal to v3 minus v3 comma w1 divided by inner product of w1 comma w1 into w1 minus inner product of v3 comma w2 divided by inner product of w2 comma w2 into w2. This is directly from Gram-Schmidt theorem. You can say Gram-Schmidt process also. This is the spelling SCHMIDT. By this equalities, we can directly calculate the values of alpha, beta, gamma, and then sum of them. We will get the answer. Is it okay?
Yes, sir.
Okay. So for the 10th problem, which of the following statement is true? We have to check the true statement. Class is over, but people are still joining. So which of the following statement is true? It is given different matrices: nilpotent, idempotent, and nilpotent and diagonalizable. So yeah, okay. So the first option, A is nilpotent matrix. Sorry, a nilpotent matrix may have a non-zero trace, but determinant is necessarily 0. So we have that whenever A is nilpotent, suppose A is of order given n cross n. If it is nilpotent, we definitely have that a power n is equal to 0. That means its characteristic equation is nothing but x power n. This is the characteristic equation. So from this we can say that the eigenvalues of A are nothing but all are zeros. So from this we can say determinant is nothing but 0 because the product of eigenvalues, and similarly the trace is nothing but the sum of the eigenvalues, that is also equal to 0. But here it is, in the first option it is said that have non-zero trace, but it cannot be possible whenever A is nilpotent. So the first option is wrong. Similarly for the second option, when A is an idempotent matrix, an idempotent matrix A is always singular. That means whenever A is idempotent, we call A is idempotent if A square equal to identity. By this we can say minimal polynomial. Here I am just writing, here I am writing minimal polynomial, here I wrote characteristic polynomial. Can you understand why I wrote this difference? Here whenever A is nilpotent, we cannot say for some value a power k equal to 0. Of course it can be equal to 0 for some value k, but we may not say it is for fixed k. But in characteristic polynomial we always have that x power n for by using characteristic polynomial we can say a power n equal to 0 because n is the order. It has to satisfy this property. But here I am just writing minimal polynomial. Of course here also we will in characteristic polynomial we will get some polynomial of order n, but we don't need that. We are just calculating the eigenvalues, so I am just writing the minimal polynomial because all the eigenvalues of the matrix has to repeat in minimal polynomial also. Yes, so from this we can see minimal polynomial is nothing but x square minus 1. That means eigenvalues are 1 and minus 1. So from this the determinant of that matrix can be equal to always plus or minus 1, because of course the eigenvalues are these two, but these can be repeated, like 1 can be repeated 2 times and minus 1 can be repeated 3 times. That depends upon the order of the matrix. But anyway, for whatever the order of the matrix, the determinant can be equal to plus or minus 1 always. But here it is they are saying is always singular, but it can never be singular because it can never be equal to, the determinant can never be equal to 0. The trace of the third option is trace of b power 4 is always an integer when b is an idempotent matrix. So we have that whenever b is an idempotent matrix, similar to the second option, we have that eigenvalues are similarly equal to 1 or minus 1 for the corresponding b. But for the matrix b power 4, we have the eigenvalues equal to 1 always. We have that whenever we have, if lambda is eigenvalue of a, that implies lambda power n let me write k, lambda power k is eigenvalue of a power k. So by this we can say eigenvalues of b power 4 are nothing but ones only. So by that, trace is always an integer. That we will get the trace is nothing but the order of that matrix b power 4. Of course, that is not given here, but order can never be rational or irrational. Sorry, it can be rational, but it can never be irrational. It is always an integer. So we can say the trace of b power 4 is always integer. For the fourth option, a matrix can either be nilpotent or diagonalizable. Can either be nilpotent or diagonalizable. So nilpotent matrix is, we have that nilpotent or diagonal. They are saying any one of these can be happen, but for the matrix A equal to 0, we have that this is nilpotent and diagonalizable also, and this is the only matrix which is nilpotent or diagonalizable, which satisfies this both. So this is option is also wrong. Is this okay? This is for the D option, this is for B option, this is for C option, this is for A option. Is it okay?
Sir,
Yes, sir.
sir,
Yes.
one request, sir.
Yes, please.
You upload this live video immediately, sir. Last week's you had not uploaded only. Last
week,
week's live class,
yes,
it
it
was
is.
not there. I checked the next day, it was not uploaded.
Maybe I uploaded after some time, I think. Okay, this video I
This
will upload it.
immediate, because tomorrow is the submission. No, sir, you upload today only, sir.
Okay,
With
but
the